One of the most prominent protocol types in decentralized finance are decentralized exchanges or DEXs. They allow people to exchange tokens for one another. So let's say you have an X token, but you want a Y token, then you can make use of these smart contract-based protocols to exchange or swap these two tokens. Now, even though these decentralized exchanges come in many different forms, there is a dominant type as of right now, and that's a so-called constant function market maker, and that will be the main topic of this video. All right, let me get started by quickly showing you where exactly on the DeFi stack we currently are. And this really shouldn't be too much of a surprise. Obviously, when we talk about decentralized exchange protocols, then we are right here on the protocol layer, and more specifically right here with the exchanges. But before we can get started and actually talk about decentralized exchanges, we have to take a quick look at centralized exchanges. Because in many ways, the shortcomings, some of the challenges and issues of decentralized exchanges have served as a motivation for and led to the creation of these decentralized exchanges. So what do I mean by that? Well, first of all, a centralized exchange is essentially a heavily centralized platform. So they have a website where you can register, where you can create an account, where you get a login, so a username and a password combination. And once you have that account, you can deposit funds, you can deposit assets with that centralized exchange. And these assets you usually deposit in the form of crypto assets, in some cases also in the form of fiat currencies. But once you have deposited your assets with the exchange, they will show up on your profile, on your account, on the website. Okay, so you see them there, and then what you can do is you can use these assets to exchange them, to swap them for other assets on that centralized platform, so on the exchange. And what you can also do is you can ask the exchange for a withdrawal. So you can say, please exchange, issue a blockchain transaction to send these funds to one of my blockchain addresses, to an external address. Okay, you already got it between the lines. And when I say you can ask them for withdrawal, what it means is the moment when you're depositing funds with the centralized exchange, you are effectively losing control over these assets. So you no longer are in the possession of the corresponding private key, because these assets now are on a new address, on a new blockchain address, on a blockchain address that is under the control of the exchange. And as a result, you cannot issue a blockchain transaction to move these funds. So you are completely dependent on the centralized exchange. If the centralized exchange is not able or not willing to give you back your funds, to keep their promise, then you will lose your assets. And unfortunately, that's not just a theoretical problem. It actually happened many times in the past. Many people rely on these centralized exchanges, and they have accounts there and store some of the funds there. And unfortunately, there have been many hacks, and there have been cases where there were rogue employees who ran with the money, and there have been cases where these exchanges, they simply lost the private keys of their customer funds. And no matter what it was, it doesn't really matter at the end of the day, because the result is exactly the same. The result is that customers who have funds with these exchanges will lose their money. Now, of course, there are also exchanges that didn't suffer any of these problems. There are heavily regulated exchanges that have good processes in place, but the general threat remains the same. And you have to consider also, from the point of view of a potential hacker or of an attacker, this really is a juicy target. It is somewhat of a honeypot, because it is a collection of many customers' funds. It's not just your funds you're having on this exchange. It's a collection where multiple people, a large number of people, are storing their funds, and therefore it is a juicy target. And it is a target that can potentially be compromised, because there are people working there, and some people, they have control over these assets. So it effectively is a single point of failure, single point of attack. And it has been historically the reason for many thefts, for many losses of assets. And that led to some frustration, obviously. And when there is frustration, people are looking for alternatives. And that essentially led to the creation of these decentralized exchanges, with the idea that the user remains in exclusive control of the assets until a trade is executed. So you don't have to send or deposit your funds to an exchange, you are in effective control, in exclusive control over your assets until the very last moment. And what do I mean by that with the very last moment? Well, at some point you're trading, for example, you're trading A tokens for B tokens, as in our example in the token video where we had Alice who had A tokens and Bob who had B tokens, and they wanted to exchange them. So obviously at some point you will give up, you will surrender control over these assets, because that's the entire idea of making a swap, of making an exchange. But what is important with this atomic trade execution, these atomic swaps, is that at the very same point in time, when you're giving up access or control over the original assets, you get access and control to the new ones. And recall that when we talked about these atomic swaps, atomic transactions, we said that these two sub-transactions are inseparable. So there is no way that only a part of that transaction can get executed. And if that is implemented properly, so if there are no coding errors, then this can effectively eliminate counterparty risk. And that is, of course, extremely exciting. Now, this aspect is one of the key building blocks for these decentralized exchanges. So the idea that you can exchange or swap these assets in a trustless manner, that you don't have to trust anyone, that there is no custodian, and that through these atomic swaps, so through the atomic exchange, the inseparable exchange of these two assets, you can effectively eliminate the counterparty risk. Now, of course, there are multiple different implementations. So when we look at this tree right here, then of course you have centralized exchanges. That's not something we're looking at right now. We are more interested here in the decentralized exchanges. What's important to understand is that there is not just one type of a decentralized exchange. There are many different implementations. So for example, order book exchanges, OTC, so over the counter and peer-to-peer exchange protocols, and you have reserve aggregators, and then there is something called constant function market maker, and that's the part we will look into in greater detail. But let me quickly start with order book exchanges. This should in fact be familiar from traditional finance. There we also have order book exchanges. In fact, most of the exchanges we are seeing in traditional finance are order book exchanges, and the idea is that people can issue orders, so that's essentially a message of the intent that you're willing to trade a certain asset against a certain other asset at a certain price level. Then you're expressing that intent in the form of an order, and in an order book, all of these intents are stored, are getting matched. So when there are two people who have opposing preferences at the same price or at an overlapping price, then these orders are getting matched and executed accordingly. And when people started to look for decentralized solutions, they quickly came up with the idea that these order books, they could be replicated on-chain, so that you're using a smart contract on the blockchain to replicate an on-chain order book exchange where every single order, so whenever somebody expresses the intent to trade, is effectively a blockchain transaction. And this worked great. Of course, it's extremely transparent. It also has been a great innovation, and it's been super exciting in the beginning, because now you had for the first time one of these decentralized exchanges where you could also list your own tokens, where you could freely, permissionlessly, and completely transparently trade with other people. But it also came at a huge cost, because what does it mean when you have when every single order is effectively a transaction? Well, what it means is that this is somewhat inefficient, and of course, especially when you have high gas prices, then it will become extremely inefficient and expensive. And why is that the case? Well, in many cases, you have to update your orders. It's not that every single order gets executed. In some cases, the prices will shift, so you want to update the order to reflect that. In some cases, your preferences may shift. Then you want to update your order to reflect that. You have to cancel it, issue a new one. And in the context of an on-chain order book exchange, every single one of these updates, every single one of these cancellations and issuing new orders has been an on-chain transaction. When you think from the point of view of a market maker, let's say, and it becomes apparent that this is extremely expensive, because market makers, they are constantly quoting prices. They have to readjust their prices, so buy and sell quotes essentially. And this, of course, requires that they're always canceling their old orders and that they are issuing new ones. That's, of course, not feasible, at least not in a somewhat efficient way, because then you're constantly updating, constantly issuing new transactions, and that would just be really expensive. So instead of relying on these on-chain order book exchanges, people had the idea that the order book itself could be hosted off-chain. The transactions, so the actual swaps, would still get executed on the blockchain, so you would have the same security guarantees with respect to the exchange, with respect to the swaps. But the order book itself would be stored in a somewhat centralized fashion. And the one drawback you obviously have with that, or a potential attack vector, is that you cannot be sure whether you are seeing the entire order book. So somebody could basically hide information from you, only show you the partial order book. That is an issue. And another issue that also you're likely facing with these off-chain order book exchanges is that the matching algorithm in many cases is also part of the off-chain protocol. When you have the off-chain, you have the order book off-chain, then also the matching is conducted off-chain. And in that way, you're not sure if you're getting the best execution, if you're getting the best price, because what could happen potentially is that someone cheats with these matching algorithms. And that is, of course, an issue. Now, to be fair, these off-chain order book exchanges, they came a really long way from their initial implementations. There are some protocols who are addressing some of these issues, and it's certainly extremely interesting, and it's certainly an important part of DeFi, but we're not specifically looking into these off-chain order book exchanges for one simple reason. I assume that most of you have a solid understanding of what order book exchanges are from traditional finance. And it's really not that different. I mean, when you have an understanding of smart contracts and when you know how these order book exchanges work, then it's simply adding one and one, and you understand how these off-chain order book exchanges work. So that's not something we will look into in greater detail, but certainly something that's also important in the context of DeFi. The next thing are OTC, over-the-counter, or also peer-to-peer exchange protocols. Now, I have to admit that these are not exchanges in a traditional sense, because when we talk about OTC or peer-to-peer, that's the complete opposite of an exchange. It's not this marketplace. What it is, it's a protocol that allows you that when you already have a counterparty, when you already have someone who has opposing preferences, then you can engage with them, and you have you could say a template for the trade that allows you to conduct this trade in a secure manner. So essentially what it is, it's just this template that allows you to do these swaps in a secure way when you have the counterparty. But it's not necessarily a protocol that tackles the issue of matching, that tackles the issues of the double coincidence of ones, or tries to find a market price. In many cases with these OTC peer-to-peer protocols, it's a negotiation between two parties. They are directly negotiating prices and then executing the trade. So that's also important, also in the DeFi space. But because of its nature, its peer-to-peer nature, OTC nature, it's not one of the dominant protocols. The next thing are reserve aggregators. That's again something that works quite similarly to what we're seeing in traditional finance. The idea is that you have this aggregator. In this context, it's a smart contract, and then you can call a function with this aggregator, and you're asking, hey, I'd like to exchange A tokens for B tokens. What is the best price you can give me? Then, of course, this aggregator has many different liquidity sources, so liquidity pools in the background, many different liquidity providers, and simply checks for a given volume the person is requesting what would be the best price that the reserve aggregator can serve. And that's the entire idea. So it's just aggregator of different liquidity pools, this aggregator that allows the reserve aggregator to make use of these different liquidity pools and quote a price to the person who is calling that reserve aggregator. Again, that's nothing entirely new. That's something we also know from the traditional finance. But of course, I'm not saying this in a disrespectful way or saying this like it's not important. It is important for DeFi. Let me be very clear on that. But it's just that people already have a solid understanding of how these reserve aggregators work, and there isn't too much to say on that, because essentially it's just liquidity pools that are connected to this reserve aggregator, and then the reserve aggregator who's quoting the best price from these liquidity pools. So the one thing we will focus on for the rest of the lecture are constant function market makers for several reasons. Number one, these are the dominant exchanges in DeFi as of right now. Number two, it's something that is somewhat new, at least. At least in this specific form, that it doesn't exist in traditional finance. Last but not least, it's also something from an academic point of view where you can say a lot about, where you can analyze it analytically from a theoretical model perspective. That's why we tackle into these constant function market makers, because it's simply from an innovation point of view the most exciting one for people with a finance background. So let me first give you the intuition. What is a constant function market maker? The first thing you have to be aware of is that constant function market makers, there are essentially three parties involved. So what you have is you have liquidity providers. These are just regular people. It can be anyone. And what they're doing is they're providing liquidity. In our simplest form, the example we will go for first, there are two tokens. So they are providing an asset pair of, let's say, X and Y tokens, and they are doing that by depositing these tokens with a liquidity pool, as you will see later on. So this liquidity pool is a smart contract. That's the second involved party. That's essentially the exchange itself, and that's where these tokens are stored. And then the last party that is involved is the trader, and trader, this also can be anyone, so there are no restrictions. They are trading X tokens against Y tokens on this liquidity pool, on this constant function market maker. So let me give you an example right here. So you have the liquidity providers in this example. They are depositing CLC, so the crypto lectures coin we've created in the token chapter, alongside Ether. From a technical point of view, this would be wrapped Ether, so the ERC20 compliant version of Ether. But let's just go with Ether right here. Okay, and then they have these two tokens. They deposit them, they provide liquidity into the pool, and then you can see right here this pool has CLC and has Ether, and for the sake of simplicity, we're just going to assume right here that there are equal proportions, but this could really be any proportion, okay? It's just that we're assuming that there are equal proportions right now, so you have some CLC and you have the same amount of Ether in the pool. What's important is that all of these liquidity providers, they are providing the same proportion to the pool. So there might be different amounts, but it's always in the same proportion, relative proportion of X and Y tokens. And what they're getting in exchange is a so-called pool tokens. Pool tokens are a representation of ownership of the liquidity pool, representation of proportional ownership. So depending on how many tokens they have contributed to the liquidity pool, they will get more or less of these pool tokens, and these pool tokens allow them to withdraw the liquidity from the pool. So when you have added some liquidity initially in the form of CLC and ETH, then you get this pool token, and you can use this pool token later on to withdraw your liquidity from the pool. Then we have the trader, and the trader, what he wants to do is he wants to get some CLC, and he does so by providing Ether. So he calls a function with the smart contract, with the liquidity pool, and sends some Ether alongside that function call. These Ether get added to the pool. So you can see the increase right here. And in return, in exchange, the constant function market maker sends back some crypto lecture coin to the trader. So that's the idea. So the trader, anyone can make use of that pool and can make use of these of the opportunity to swap these tokens. So what's important to understand, first of all, is that the price is determined endogenously, and it is a function of the contracts of the pool's token holdings. So depending on how many tokens there are left in the pool for X and Y tokens, or here for CLC and ETH, this determines the price the trader has to pay. Intuitively, and you will see later on why this is the case, the less tokens of one kind are in the contract, relatively speaking, the more expensive they get. So in this situation right here, where CLC amounts drop down a little bit, when there would be an additional trader later on, and that would be the current state, then this next trader would pay a higher price if he would also want to take out some CLC, because relatively speaking, CLC got rarer. There aren't that many CLC, relatively speaking, in the pool anymore when compared to ETH. And the second thing that will become important throughout the lecture is that there is a small fee charged for each trade, which leads to an increase in the pool reserves. This ensures that the fee is distributed proportionally to all liquidity providers. Why is this ensured? Well, simply because you remember that they have the pool tokens, and these pool tokens, they are proportional claim on whatever is stored on this liquidity pool, on whatever is stored on the CFMM. And obviously when this is increased, so when there are more tokens in the liquidity pool and these people have proportional ownership, then their personal holdings will also be increased proportionally. Now, initially for our first few examples, we will ignore these fees just for the sake of simplicity, and that we can start out relatively simple and then build on it. But you will see later on that these fees play a really important role for the liquidity providers and are, of course, an important incentive for them to provide this liquidity. Now, one more thing you have to understand is when there is an endogenous pricing, of course, that does not mean that it's completely independent of the outside. And in fact, it's by design that it's not. There is always a market price when you have an important token. Unfortunately, not for our crypto lectures coin, because this token isn't traded anywhere else. But let's go with a stable coin, let's say ETH pair. And then, of course, you have prices for Ether on various exchanges, and assuming that the stablecoin really is stable and is pegged to the US dollar, then of course it's just the US dollar price for Ether that would be relevant. And when you have that price on various exchanges and centralized exchanges and other decentralized exchanges, then of course there would be an arbitrage opportunity when the price on the constant function market maker is not in line with the rest of the market. So let's say the rest of the market moves and the constant function market maker would remain for a certain period of time on its current price point. Then there would be an arbitrage opportunity because there's a price difference on these various exchanges, and people could simply make use of this arbitrage opportunity, make some money from it, and by doing so they would move the price on the constant function market maker in line with the market price. And that's the entire idea. In that way, you don't need any price oracles, external data feeds that give you information about the prices. It's really this self-sufficient system where the prices are determined endogenously just by incentives given from the open market. And that is somewhat exciting. All right, and with that, we can get started with the math, and we start with a really simple case with the constant product market maker. This is just a special case of the constant function market maker, a special case because it uses a specific functional form, and it has its name because right here, as you can see, we have a product x times y equals k. And what do these variables mean? I mean, when you have a lowercase x really represents just the amount of uppercase x tokens. So uppercase x is just a token type, and lowercase x represents how many of these uppercase x tokens are in the pool, so are on the constant function market maker. Equivalently, when you have lowercase y, that's just the amount of uppercase y tokens, so of the type uppercase y in the pool, so on the constant function market maker. And k is simply constant. So the pool holding, the constant function market maker holdings, in this case, when you're using a constant product market maker formula, means that there can be any combination of x and y tokens as long as these two amounts, so x times y, are equal to the constant. Okay, so there is this constant k. That's basically the representation of the potential of the possible allocations in the pool, and you can have any combination of x and y token amounts that satisfy this constant right here. Now, this also determines the prices, of course, because when you have this relationship, what you will end up with is when you have a price for x, so px, this will equal to y divided by x. And when you have a price for y, this will equal to x divided by y. And this makes a lot of sense also intuitively, because when you have a price for x, let's say, and the number of x tokens in the pool would increase relatively, then what would happen? You would have a higher number where this gets divided by, and when it's getting divided by a higher number, then of course the result would be smaller. So more x tokens means that you have to pay a lower price for these x tokens. Whereas when there are less x tokens, then it would get divided by a lower number. And this would mean that it would be a higher price. So less X tokens in the pool would mean that you have to pay a higher price for these tokens. And here equivalently, of course, for PY, so for the price for the Y token. Now, if you want a more mathematical derivation, when you rearrange the equation up here, and you effectively say that you have y as a function of k divided by x, and you take the first derivative of that, then what you would end up with is the additive inverse of this price right here, and that essentially, as you will see later on in our graphs, represents the slope. So it's just the additive inverse of that, okay? So when you draw that, the information we have so far, and then again here on the x-axis you have the x tokens, uppercase x tokens that are in the liquidity pool, and of course that's represented by amount x. And here on the y-axis you have the uppercase y tokens in the liquidity pool, and of course that's represented by lowercase y. Then you end up with a certain point right here, and this point, as you know, has to satisfy the condition that it has to be equal to k. And when you're drawing all of the potential points of k, then you're ending up with this convex curve right here. I'm really inaccurate with my laser pointer, I apologize for that, but I think you get the point right here. That's essentially the potential allocations for X and Y tokens in the pool. Okay, that's the idea, that's the relationship. So any one of the points on this curve would be feasible allocations in the liquidity pool. Now, when you have a relationship like that, so when you are going with this functional form x times y equals k, then of course this curve will be convex. So you have essentially an indifference curve, again right here, the blue curve, a convex one. And what's also, and I already mentioned that, is that the pricing of this pool would be endogenously given using this price relationship we have defined on one of the past slides. And what's really important to understand is with that pricing scheme, the pool will never be depleted by a trade. So when people are swapping, this swap cannot lead to a situation where there are no tokens of one type in the pool. Of course, with one exception, it's subject to the decimals and to the overall liquidity. When you have, for example, a really low overall liquidity and you're not allowing for any decimals, let's say, then there might be situations where it could get depleted. And also, for example, when you're only allowing for four decimals or something like that, or even with 8 decimals, then in really extreme cases, it could be possible that the pool is running out of liquidity, so that it couldn't trade any additional tokens anymore, simply because it doesn't have enough decimal places. But other than that, it's not possible, because the less tokens of one type are in the pool, the higher the relative price for that token will get, and therefore the pool, the CFMM, with a constant product model, will always be able to quote prices. So let us go with a first example. So let us go with a swap. And again, here for our initial example, we're assuming that there aren't any fees whatsoever. We will introduce them later on, but for our first example, just for the sake of simplicity, we will ignore these fees. So let us assume that there is a constant product market maker with no fees. Suppose a trader wants to exchange or swap delta X of these X tokens into Y tokens. So the trader is providing delta X to the pool, and he wants to take out a certain amount of Y tokens, which is denoted by delta Y. And this will always be seen from the point of view of the pool. So of course, later on, we have to deduct these delta Y tokens because they're getting paid out. So what would happen in this case? What would happen is we again have this starting situation right here, and then the trader is adding delta X to the pool. Okay, so the pool holdings, the constant function market maker holdings, would increase to that point. And then since you have to stay on the curve, it's not that big of a surprise. What you would end up with in terms of the allocation is this Y prime right here. So that would be the new holding of the whole new holdings of the pool. So this would be Y minus delta y, and delta y, of course, is whatever the pool would pay out. So that is what the trader would get. So from the point of view of the pool, and that's what we're looking at right here, you're obviously deducting these delta y amount of y tokens, but the trader, from his or her point of view, he or she would get this amount of delta y tokens in exchange for the delta x tokens. So the token y, uppercase y, pool reserves after the trade would be denoted by lowercase y prime, and this is equal to k divided by x plus delta x. That's kind of straightforward, because obviously x plus delta x would be the new x amount, and if you divide the constant k by the new token holdings in x of the pool, then obviously you will end up with the new token holdings in y. So you could make the argument that x plus delta x right here, you could also denote that by x prime, and then it becomes even more obvious, because then you would divide k by x prime, and that clearly is a y prime. So the change in token y reserves is delta y, and delta y obviously is y minus y prime. That's what we just did. So the constant k after the trade, which is k prime, would be x plus delta x, of course in brackets, because that's just the amount of x tokens after the trade, and times y minus delta y, again in brackets, because that's the amount of y tokens after the trade, equals k. So that would be the relationship, and this means that, of course, since we haven't changed anything about k, since you always have to remain on that constant k in the absence of fees, that k prime right here would be equivalent to k. There would be a different allocation, there would be a different essentially mix of x and y tokens. It would not be the same ratio, the same relation, but the k would not be changed by that. Now let's look at something that's called slippage. And slippage, that's now from the point of view of the trader. We're still looking at the pool, don't get me wrong, but slippage is something that is important for the trader, because obviously the trade, the swap he or she is conducting, has an effect on the prices. So it will change the pool ratio, and since the price is just a function of the pool ratios of the two token amounts, his or her trade will have an effect on these prices. So when you have this change right here, so when you're going, when you're adding these delta x tokens to the pool, and when you're taking these delta y tokens out of the pool, then you essentially have this as a starting point right here. That's the point you're ending up with after the trade. And what you have to look at is the tangent of the starting point. The tangent of the starting point, as I said earlier, is essentially just minus p of x. Recall that the pool ratio p of x is defined by y divided by x. And then when you want to have the effective swap price, and that's the price you actually are paying, you have to take the line between this point right here and this point right here, and look at that ratio, so basically the slope. And this is px bar, so that's the effective swap price, and you get it by dividing the delta y by delta x. So that's the effective swap price, and intuitively you can think of that as the average price you're paying for the trade, because along this line, whenever you're trading, when you're starting here and you're going down the curve, and then if you would divide that into multiple trades, then for every single trade you're conducting, the price would get a little worse and a little worse and a little worse and a little worse. Why? Because the tokens you're taking out, they get rarer in the pool. And when there are less of these tokens in the pool, then the price, of course, increases. But since you have just one transaction, it's an average price, and this average price is represented right here by this slope, and essentially by px bar, that's the effective swap price. And of course, this price is worse than the pool ratio up here, so this would just be the price for a infinitesimal, for a really small trade, for essentially infinitely small trade, but something that you cannot really achieve, something that whenever you are effectively trading a positive amount, then you will never be able to achieve that price because you're moving away from that point. And this effective swap price, it depends on the amount, it depends on the relative amount you're trading compared to the liquidity pool holdings, okay? So what you end up with is this relationship right here when you're taking your effective swap price and divide it by the pool ratio, so by the PX price, then you're ending up with the price slippage. And the price slippage, we define it as S, is the price deviation from the infinitesimal trade PX to the actual trade PX bar, and the smaller trade size relative to the pool liquidity reduces this price slippage, obviously. So the pool ratio after the trade is conducted, and that's the last thing in this graph right here, we call PX prime. And PX prime is just y prime divided by x prime, or in other words, y minus delta y divided by x plus delta x. And you can again see the slope here, that's minus px prime, okay? That would be, again, the inverse of px prime right here. So let us now introduce fees, and we're doing that with a new variable right here with rho, and rho essentially represents this fee, and it is a value in between 0 inclusive and 1 exclusive. So obviously they cannot be 100%. If you're paying 100% fee, then it would not be too much fun to trade on this exchange. And there is a corresponding factor, gamma, and this factor gamma essentially is just 1 minus rho, so that's what we will multiply some of these numbers later on when we want to deduct the fee. Okay, that's why we are expressing it in that way. The fee is charged on every trade and added to the liquidity pool, and therefore leads to an increase in K. Okay, so K will now increase with every single swap. Because of this fee, whenever trader pay a fee, then this fee will get accumulated in the liquidity pool, as you will see. What's super important to understand is that protocol fees, so fees of these constant function market makers, rho we are talking about right here, are not the network fees you're familiar with from previous videos. The network fee is something you pay to the miner, so you pay for your transaction being included in a block. But the protocol fee right here is essentially a fee you pay to the protocol, to the smart contract, to the exchange for taking the service of swapping that. Okay, that's the idea, and it is important because it serves as an incentive for the liquidity providers to contribute to liquidity because they can earn something. Now, we will go with some really high examples later on when we look at numbers like 20% fees and so on. Obviously, that has nothing to do with reality. In reality, these fees are really low, like 0.3% or even lower. But it's just for the visualization and for the sake of simplicity in our examples, we will use relatively straightforward numbers, as you will see. But let's first start with a theoretical point of view. Again, here you have our initial points. So just the constant function market maker, the constant product model relationship with X, Y, and K. And again, we assume that somebody is swapping X tokens against Y tokens. So the trader is contributing delta X to the pool. And then what happens, and that's different to what we've seen previously, there will be a certain fee deducted. And the way it's deducted is we take X, so the initial amount, plus gamma times delta X. And of course, since gamma is a value between 0 and 1, this will be something that is lower than when you would just add delta X to X. So it will be somewhere in between. And the difference here, which is represented by the red arrow, as you will see later on, that would be the fee. Now, what's important to understand is that the pool, the liquidity pool, still gets delta X tokens. So that's what the liquidity pool got. But for the computations of Y, So basically for the computation of what the pool is paying out to the trader, the pool will use this value right here, so x plus gamma delta x. And when you're using that for computing the amounts of Y tokens that will get paid out, so Y prime rho indicating that it's considering fees in this case, you will use this intersection right here. So the intersection between K and this X value we have determined, and then you will end up with this Y prime rho, okay? Now, what happens then is, obviously K is increased because you're taking it deducted, so only a partial number of these X tokens that you actually got, and use it to compute whatever the pool is paying out. So obviously this will lead to an increase of K, and the way this looks in the graph is that you have a new K, let's call it K rho prime right here, and you're taking the new amount of Y tokens, so that's Y rho prime right here, and the intersection of the new token holdings of X tokens. Recall, even though we used this value right here, so the lower value to compute how many Y tokens get paid out, these are the actual token holdings. So we know that the new K rho prime must be at this intersection. So you have this point right here. Okay, and again, when you have this K, so you get the new K from the new Y, the new X, then you know that's the new constant, and then everything on this new line would be a feasible allocation for this pool. So that's how the K gets increased through these fees. And recall that people, they have these liquidity pool tokens, they have these shares, the liquidity providers that represent partial ownership to the liquidity pool. Obviously, when you have an increase like that, then their proportional shares will also increase depending on how many liquidity pool tokens they currently hold. So as I said, that right here is the fee that the trader is paying to the pool, and essentially the amount that is increased in the liquidity pool. So the two token Y pool reserves after the trade, so that is Y rho prime, would be equivalent to K divided by X plus gamma of delta X. So that is what would be in the pool. Why is that the case? Well, because in order to compute these Y tokens, you're using the deducted value, so you're using the lower value, which is gamma times delta X. So that's what you're using. Even though you have more X tokens in the pool, that's what you're using to end up with the Y value in the pool, okay? And that's why you're computing it that way. Because when you're taking K and divide it by something that is lower than what actually is in the pool, and they're doing that again by the factor gamma, then you're ending up with something that is a little higher than it should be with a constant K, and that is essentially what will lead to this increase in the new K. So the change in token Y reserves is you have delta Y rho, and this is of course equal to Y minus Y rho prime, and I think that's quite obvious. That is essentially just the difference, so that's what you're paying out, the delta Y rho. And then last but not least, the constant K, and that's what I already said several times, there is a new K. So you start out with a K, with the regular K, and you end up with the K rho prime right here, and K rho prime is defined as X plus delta X. So you get the entire amounts of X tokens that are deposited with the liquidity pool, and you multiply that with Y minus delta Y rho, and recall that this is a little lower than what it should be with a constant K. So obviously what you know from that, is that K rho prime will be larger equal to K, depending on the size of the relative fee. So let's take a step back once again. This is just the initial situation. So this would still be without fees. And now we're going to add fees on top of that. Recall that without fees, you had the initial pool ratio right here, which is Px equals y divided by x. Then you have the swap price, the effective swap price, which is just delta y divided by delta x. And then you have the price slippage, which is just Px bar divided by Px. Now, when you have a fee, then you get this new curve. And obviously the effective swap price would be right here at this point. So you get the effective swap price by connecting these 2 points. So the initial allocation with this point on the curve right here. Why is that the case? Well, because this is the token amount, delta y rho is the token amount you get paid out as a trader. And of course the delta x right here, that is what you have deposited with the pool. And if you combine these two, then you would end up in this point. And thereby you can get the effective swap price by dividing delta y rho by delta x. Okay. Then when you look at the pool ratio after the trade, and that's the tangent right here, then you get this P of x rho prime by dividing y rho prime by x prime. And this essentially is just y minus delta y rho divided by x plus delta x. And that's the pool ratio after the trade, which happens to be the inverse of the tangent in this point right here. That's essentially the price point you have after your trade has been executed. And then you also have the fee effect, and the fee effect you get when you're comparing what you would get in a situation without fees to what you would get in a situation with fees. And notice that the difference essentially is in the delta y, so in what you're getting paid out. We denote this fee effect by C rho, so the cost of the fees, C rho, and this is equal to Px rho bar divided by Px bar. That's how you get this fee effect, also something the trader pays. So essentially the trader has two things he or she must consider. Number one would be the slippage, we already know, and number two is the fee effect. Now let's look at all of these variables once again. You have the price ratio, the effective swap price, ignoring fees, the effective swap price including fees, price slippage fee effect, and price slippage plus fee effect. This essentially is just a cheat sheet, not for the exam to be clear, but just for studying. For your handout, we already tackled all of these things on previous slides, but it's just much more convenient if you have them on one slide, I'd say. So let's go with an example with numbers now. Imagine a situation where you have a liquidity pool where currently there are two tokens, so X tokens and Y tokens, and the amounts in there is 10 each. So lowercase x would be equal to 10 and lowercase y would be equal to 10. And what you're doing now is you're increasing the X amount to 15. So there is a trader who deposits 5 X tokens with the pool, and then you have the fee deducted. How do you do that? Well, we assume there is a 20% fee in this case in our example, which is of course excessive, and this has nothing to do with reality. Again, in reality, fees are more closely to 0.3%, but the reason why we're going with a large fee like that for this example, for a number example, it's just because otherwise we couldn't visualize it, and it's just much easier for demonstration purposes when you have a high fee like that. So how do you compute it? You have essentially x plus gamma delta x, and this is 10 plus 1 minus 0.2, so 1 minus rho is 0.2, and then times 5. And this is equal to 14. So instead of these 15, you know that you're here at 14. That's what you're using to compute whatever gets paid out in Y tokens. How do you do that? The original Y prime, so that would be without fees, would be 100 divided by 15. And then you would end up with 6.66. the original delta y would be 10 minus 6.66, so it would be 3.33. But now when we are considering rho, so when we are considering the fees and we have y rho prime, then you would end up with 100 divided by 10 plus 0.8 times 5. That's the equation from the previous slide. And you would end up with 7.1429. So that's the new y prime when you are considering fees, so y rho prime. And for delta y rho, so the change in y tokens considering the fees, that would be 10 minus 7.1429, and this would correspond to 2.8571. Now, when you look at the new k, how would you get the new k? Well, k rho prime, that's essentially 15 times 7.1429. Of course, you're using the 15 now, not the 14, because from the perspective of the pool, you still get the entire 5 X tokens, but you only lose the deducted amount, so the smaller amount of Y tokens, and that's why you end up with 107.1435, and that's of course larger than what we had previously. Previously you had 10 X tokens and 10 Y tokens, so the original K was 10 times 10, which obviously is 100, and now you have a K rho prime, so a new K of 107.1435. So the PX, the original price was 1. The effective swap price you got in this case is 0.6667. The effective swap price considering fees, so the PX rho bar would be 0.5714. And then the new ratio, so the new price PX prime would be 0.381. The slippage would be 0.6667. The cost of the fee, so essentially the fee effect, I should say, would be 0.8571. And when you combine the two, then you have to multiply them. So when you have the fee effect and the price slippage, then it would be 0.5714. Or what you could also do alternatively is you could take these 0.5714 divided by 1. So that's essentially this price right here. This one, so the effective swap price considering the fees, 0.571 divided by 1. So that is the original price right here, and then you would end up with the same value. So the next thing we will look at is liquidity provision. And I said in the original example that anyone can contribute liquidity to the pool, so there are no restrictions. Anyone can just do that. And they can do so by providing n uppercase X tokens, so n amount of these type X tokens, and n times Y divided by X, so that's essentially the price, uppercase Y tokens to the smart contract. This has to be in this specific ratio because that's the current price, and you cannot just contribute a random ratio of these X and Y tokens. Obviously, it has to correspond to the current ratio, but you can scale it, so you can contribute more or less depending on your own preferences, but it has to be in this fixed ratio. The liquidity provision can only changes the token amounts and the constant K. It does not change the ratio, obviously, when you're providing the same ratio. The ratio between the two tokens, as I said, remains unchanged. And both reserve factors are increased by the factor variant fee, which means that there is an increase of delta X divided by X, and this increase in delta X divided by X is the same as the increase in delta Y divided by Y. So this relation has to be the same because the ratio is the same. Then X prime after the liquidity provision, so here we're not talking about the swap, here we're talking about the liquidity provision, would be X plus delta X, which is 1 plus variant fee times X. and of course equivalently for y prime, which would be y plus delta y, or alternatively 1 plus variant phi times y. The k, so k prime, that would be 1 plus variant phi squared times k. Why is this the case? So essentially when this right here is x prime and this right here is y prime, then obviously when you multiply the two, then you end up with this right here. Then you would have 1 plus variant phi squared because it's in both of them, and x times y, that would correspond to k. So that's how you end up with this 1 plus variant phi squared times k. So when we look at the graph once again, what happens in the case of a liquidity provision? Well, it's relatively straightforward. What happens is you're starting with the point 0.0, and you're essentially going through the current allocation point, and that is the way you can scale. So anything, any point that is on this line essentially is a feasible allocation, is a feasible increase in liquidity. So when you're increasing x with delta x, for example, then you know that the intersection right here, this intersection essentially gives you the y prime value. Then you know how many y tokens you also have to deposit with the account. And that's given, of course, by k. That's given by whatever you're paying, whatever you're depositing in x amounts, because this ratio, the ratio between these x and y tokens, is fixed. Now, one thing that's extremely important for liquidity providers is called divergence loss. And that's essentially a way in which liquidity providers can lose some of their value when they are contributing liquidity to the pool. We go with a simplified assumption. We assume for this example right here that there are no fees, and we assume that there are no other liquidity providers. So we just essentially say there is a single liquidity provider for our computations. This makes it much easier, but none of this has any loss of generality. When you would consider the fees, there would be an offsetting effect to what we are observing. I will talk about that later on. And when there would be other liquidity providers, then you would have just to go with proportions. Otherwise, the general intuition and the situation would not change. So how does it work? Well, assume a situation where we provide 10 units of token uppercase X and 10 units of token uppercase Y, and we say they are equal in value. So Px equals 1, which is Y divided by X. And when we look at the equation, then we have k equals x times y. Obviously, then 10 times 10 would be 100. So we know that k would be 100. Now let us further assume that the price of uppercase X doubles. So P of Px prime would be 2. And what does this mean? Well, then you would have x prime, which is just a square root of k divided by px prime, or in other words 100 divided by 2, the square root thereof, and this would determine the new x prime value right here. This would be 7.0716, and to get the y prime value, you would take k and divide it by the x prime value you have just computed right here, and this would be 100 divided by 7.0716, which will be 14.141. Okay, so now you have the allocations. Yeah, now you know well, with the X token amounts and the K, and essentially given by the price, we have determined up there the allocation of these different tokens. Now you also know the price, so the total pool value expressed in units of token Y, uppercase Y, would be X prime times the price of X, obviously, plus Y prime, because here we don't have to do anything. It's already expressed in Y tokens, essentially, and that's not surprising. What it would be is 2 times the Y token amount, so Y prime. Why? Because by definition, whatever you have in the pool in one token should be worth equivalent amount of the other token, so you might as well just go with 2 times Y prime. And that's the value of the pool. So when we go with our numbers, then we have 2 times 14.141, which is 28.1762. Now, in order to determine whether you made a loss, whether something bad happened, we have to compare that to a situation where we didn't provide liquidity. So if we simply held our initial allocation and did not provide the liquidity, we would still have 10 tokens of both, so 10x tokens and 10y tokens. So the value of the hold strategy would be x, the initial x, not x prime, times the new price, because obviously we cannot do anything about price, so it would still be times px prime plus y, again the initial y, not y prime, because we have these 10 tokens from your holding. So this in numbers would be 10 times 2 plus 10, and this would lead to 30. So the value of our hold strategy would be 30. When you compare that once again to the 28.1762, then it becomes apparent that in this case, it would have been a better strategy to just hold on to our initial allocation. The difference between the pool value and the hold value is called divergence loss. So DL here, we denote it as DL, which is just the value pool divided by the value hold minus 1. And here in this case, you made a loss of 5.72%. And the intuition behind that is that essentially when you're moving away from the initial ratio, then it happens that you have less of the tokens that turns out to be more valuable. So whereas when you just have hold on to your initial allocation, you would have an equal the initial allocation of these 2 tokens. So the more valuable token, you wouldn't have any less of them. And that's why you're better off when you're just holding the tokens compared to when you are adding the tokens to a liquidity pool. But that is, of course, assuming that there aren't any fees. In many cases, you will be overcompensated by the fees. So the liquidity providers, when they're adding, they essentially have 2 potentially offsetting effects. On the one side, they are at risk of experiencing these divergence losses. On the other hand, they also, depending on how actively the pool is being used, they get some fees. And depending on what is larger, so whether it's the divergence loss or the fees, they can make a profit or will make a loss. Okay, that's essentially the question they are facing, and essentially the risk when you're contributing liquidity. So to be profitable, a liquidity provider must overcompensate any divergence loss DL with the accumulation of fees. And the divergence loss, and that's important to understand, is only realized when you're closing the position. So it's also called impermanent loss, because when you're not closing, then it's something that on paper, of course, would be a loss. But it could be possible that the price ratio moves back in the original direction, so that it's similarly to what the original price ratio was like. And when it's moving back, then of course you will not experience that loss. So if the price ratio between the 2 pool assets remains constant, or also if it returns to the initial ratio at the point of investment, then there will be no divergence loss. But it's important to understand that it is a risk. And obviously the divergence loss, the risk of experiencing divergence losses is really high for highly volatile trading pairs. And it's less risky when you have, for example, 2 stable coins that should, assuming the peg of both of these stable coins hold, maintain its original ratio of 1:1. Okay, and then you have a lower risk of experiencing a divergence loss. This right here is the graph for the divergence loss. So when you have an initial allocation, let's say it's 1 by 1, then that's the price ratio essentially. Then of course the further away you remove from this price ratio, from this initial price ratio, the higher your divergence loss will be. In an extreme case where the price ratio would be 0, of course you would lose 100% of your initial allocation value, because you would only hold the token that isn't worth anything compared to the other token. And in that case, your divergence loss, as I said, would be 100%. And equivalently, when you wander off too far in the other direction, then of course you will also experience these losses, these divergence losses. So in an ideal scenario, in an ideal world for the liquidity providers, the price ratio would always move around here and go always back to this initial ratio, which is just a normalized one right here, and not move too far away. So you wouldn't have any consistent price increases for one asset compared to the other asset. It should always be in the well, at least in a range of the initial price ratio between these two assets. And that would be a perfect situation for the liquidity provider, because in that case, the divergence loss would be relatively limited. Now, there are alternative functions as well. So the constant product model we have seen is just one of these functions, and depending on what exactly you are using as a pair, there might be functions that are better suited for these specific pairs. So they're all different functional forms, different parameters, and different with different corresponding trade-offs. For example, there is a stable swap invariant. You can see in the graph as a red curve. It has a relatively large area of the curve that doesn't really reflect any price changes, because it is an application for stablecoin pairs, and there it's important that, assuming again that the peg holds, that you can get this 1-to-1 ratio, this 1-to-1 price for a relatively high volume, whereas when you would have the constant product model from the implementation we just looked at, there would be a relatively high slippage for a stable pair, and this is of course not attractive for the traders. Therefore, people would turn to other exchanges where they don't have that. So that's why this stable swap invariant might be a good solution for stable pairs. Then, of course, you have things like constant sum, although it's somewhat problematic because when you're not having the exact same assets, so even for two stable coins, when they have different risk profiles, when they have a different reputation, then you will always end up in a scenario where there is only one of the tokens left, and that's the token that is generally seen as the riskier one. Token that has a better reputation would of course be taken out from this liquidity pool in this case. Okay, but there are different functional forms. That's something where people are constantly researching. And you don't necessarily have to go, even though it's the most common one, but you don't necessarily have to go with the simple x times y equals k relationship. Then there is a new concept that was introduced with Uniswap version 3 in March 2021. That's concentrated liquidity. You have to understand that the liquidity providers can add liquidity within a certain price range. So they can say, I will only contribute liquidity when we are between PA and PB. So that's the price range. And the position is active as long as you are within this range. So when the price is within this range, and it will become inactive when you are outside of this range. Inactive effectively means that the liquidity provider will only hold one token, because when you're outside of the range, then essentially the entire allocation is just in one token, and it becomes inactive, meaning that the person cannot participate in the fees anymore. So that's what I just said. If the price is out of range, the liquidity provider only holds one asset and does not collect fees. So what are the implications of this concentrated liquidity? You have a higher capital efficiency when you're doing that. Liquidity providers with concentrated liquidity earn more fees when they are within this range, but of course they also have a higher risk of a divergence loss and the risk of inactivity. Why a higher range of divergence loss? Simply because any price move has a larger impact on their position when they have a narrower range, and when the actual price, when the ratio moves outside of their range, then they are first of all inactive, they're not participating anymore, and also of course they only hold one of these assets because they are at the border of their range where the entire allocation is in one asset. So how does it look like? Usually when you're having a full price range, then you have the liquidity from 0 to infinity. But what you can do is you could, as I said, define this range. So you could say, okay, I'm only contributing liquidity between price A and price B. then of course your capital efficiency for that range is higher. But more importantly, from the point of view of the entire pool, what would happen in this case is that the aggregated liquidity positions, assuming that you have one person who is in the light mint right here, so in the light green tone, would provide liquidity for the entire range, and then you have an additional person in the darker green that would only provide liquidity between the range of PA and PB, then you would have a situation where the liquidity for this range in the pool is increased. So that as long as the pool is trading in this range, there would be more liquidity, meaning that whenever somebody swaps, that their swap would have a lower price effect, a lower price slippage, when they are simply trading in this range between PA and PB, because there is more liquidity in the pool. Okay, and also of course assuming that this is the same amount of liquidity these two people are contributing, then the person with the darker green liquidity position, the liquidity they have provided would be more effectively used when they are within this range, whereas the other person in the lighter mint green tone would have the advantage that when the price ratio moves out of this range between PA and PB, their position would still be active and would still earn fees, even though it's outside of the range of the other person. There also is an extension where you have pools with 3 or more assets. So far we have only looked at pools with 2 assets. But of course, that's not a restriction that always has to hold. The constant product function, as we have seen and as implemented on Uniswap, can be extended to pools with more than 2 assets. And the way this would work is you would have the product of xy with I from 1 to n. And this has to be k. So you could also say for 3 assets, it's simply x times y times c. And so on. So there can be any number of assets larger to, and they would still be equal to the constant in a multiplicative relation. So the product of all of these different assets. N is the number of token types of assets in the pool. Lowercase x, y would be the token amount for asset I, and k would be the constant again. So it's quite, I mean, when you're just using 2 assets, so when there is n equal to, that would be the exact equation we've looked at earlier. So another extension is the constant mean function. This essentially is just a special case of the constant product function that allows for different weights for these different assets. So this is denoted by wi, which is the weight of asset I. So let me give you an example. Let's say you have 3 different assets. Then you could have 2 assets that make up 40% of the pool value each. And then you could have a third asset that would make up 20% of the pool value. And that way you have different weights for these different assets. Now the relationship between the constant product and constant mean function is such that the constant product function corresponds to the constant mean function with equally weighted assets. So wi equals 1 for all I, or I could just say that all wi have to have the same value essentially, so that the weights are equal for all of these different assets. Now another thing you have to be aware of is that there are DEX aggregators. With DEX aggregators we are of course on the aggregation layer up here, and what they are doing is they source liquidity from different DEXs, from different decentralized exchanges, and they allow users to compare different swap prices and to choose on which DEX they want to trade and they want to swap. In many cases they make use of different DEXs just within one trade. For example, when the slippage for one DEX is too high, then they will take a partial execution on that DEX, and within the same transaction they will partially execute the rest of the trade on a different DEX. There are of course certain drawbacks also to this approach. For example, the transaction fees usually are much higher when you're using an aggregator like that, because of the aggregators overhead first of all, and then second, when they're using multiple exchanges, then of course these are multiple calls with these smart contracts. Even though it's within the same transaction, it still leads to higher gas costs, so the higher transaction cost. But still an interesting concept and something you should be aware of that it exists. And of course, a great example of composability when you can, within one transaction, use multiple different exchanges. This also leads to another topic, which is front-running, back-running, and sandwich attacks. You have to understand that whenever you're doing something on a decentralized exchange, this is done through a transaction. And these transactions, they have a life cycle that when you're initiating them, they get propagated throughout the network. Everyone can see them, so everyone can see your intention, and they're part of the so-called mempool. And there are many people who are observing the mempool, who are looking for your intent to trade, and will be trying to front run, back run, or sandwich attack you. Front running essentially means that when you get a good price, when they see that you get a good price compared to the market price, then they can actually check that. And if they would like to execute a trade before you, they simply set a higher tip or a higher gas price and hope that their transaction will be included in the block before your transaction is, or will have a higher priority within the block. And if that's the case, their trade will be executed before your trade, and they will get the price, whereas your execution will already be subject to the new price when you're moving down the curve. So it would be subject to px prime in our case. That would be your starting value, whereas you originally thought you would be starting at px. Okay, so that would be front running. Back running is a different scenario. Back running is when you're assuming that you currently are at the market price, and then you're trading, and you will shift away the constant function market maker's price from the current market price. Then people may have an incentive to try to get a transaction in immediately after your transaction, because effectively you're moving the price from the constant function market maker away from the market price, and they could profit from that with arbitrage when they're immediately executing a transaction after yours. So the goal of a back-running attack is to get a transaction in immediately after your transaction within the same block and basically make use of that arbitrage opportunity. It's not really an attack, I shouldn't say that. It's just making use of an arbitrage opportunity. But now we get to something that certainly is an attack, and that's a sandwich attack, and it's a combination of front running and back running. And you have the initial situation where a victim wants to swap X tokens for Y tokens, and the attacker observes that in the mempool and issues two transactions with the goal to front and back run the victim, so do both. And the way it works in terms of the execution order is, at least that's the hope of the attacker, is that the first transaction that gets executed is the attacker's transaction. So the attacker shifts the price. Let's say you have expected to get this price right here, so the tangent of this point, and then the transaction of the attacker gets executed first, then the price is shifted. That's the position where your trade would be executed, so that's number two. And obviously you're getting a worse price because it's the starting point would be the tangent right here. So that would be your trade right here, where you're going to X2 and Y2. And then what the attacker could do in a third transaction is having the second transaction to buy back the tokens from the first attacker transaction at a lower price. So essentially he sandwiches you, makes use of your transaction to have a situation where he first moves the price away from the market price, uses you to further move it away, and then get a better price because he can go back from that X2, Y2 value to the X3, Y3 value. And that, of course, would be profitable. Now, what you have to be aware is that, of course, this is a highly competitive business. This is free for all. You would not just you, anyone could observe that in the mempool, and there are multiple bots who are looking for these opportunities. And the way you can defend against that is you can say a maximum slippage value on these exchanges. You can say, okay, I'm not going to tolerate any slippage. And when you're not tolerating any slippage, then obviously this move from X0, Y0 to X1, Y1, where X1, Y1 would be the starting point of your trade, would make your trade invalid. you are at risk then of having a failed transaction, which of course has some transaction fees as a consequence, but at least the trade would not get executed. And even more importantly, from a game theoretic perspective, you don't give anyone the incentive to sandwich you because they know your trade is going to fail, so the sandwich attack will fail. Okay, so that's the idea. Another thing you have to be aware of are so-called vampire attacks and liquidity mining. This emerged in the context of DEXs. It's not something that's exclusive to decentralized exchanges, but the most prominent example and the first example of these vampire attacks happened in the context of decentralized exchanges. Now, I have to give you some background. So, first of all, again, you have these liquidity providers right here. You have an initial liquidity pool. And of course, these liquidity providers, they provide liquidity to that pool. And what they get in return, as we have described on one of the first slides in the slide deck, is they get a liquidity pool token. Okay. Now imagine a situation where there is a vampire protocol. This could be just a fork of this original protocol right here. So it's essentially the same decentralized exchange. And this vampire protocol simply wants to get the liquidity from the original liquidity pool, so from the original decentralized exchange protocol. And it needs some strategy of how it can achieve that. And the way it is achieving it is through giving these people, these liquidity providers, incentive to deposit their liquidity pool tokens. So from the original protocol, that is, from this protocol right here, these liquidity pool tokens they have received to the vampire protocol right here. So that's the idea. There is an incentive in place that these people, these liquidity providers, they deposit their liquidity pool tokens with the vampire protocol. And the incentive is that they get vampire protocol token rewards. So the vampire protocol essentially says, hey, I'm exactly the same protocol as the original liquidity pool, as the original constant function market maker on the left side. But besides anything you can do with that protocol, I'm also giving you additional incentives and you get some stake in my protocol. And initially, before we even get started, all you have to do to get these incentives, to get some say in this protocol, to get governance tokens from this protocol, is you have to lock up your liquidity pool tokens from the original protocol on the left with my vampire protocol. Okay? And then at some point later on, usually at a specific date, this vampire protocol will use all of these liquidity pool tokens which are stored on the smart contract of the vampire protocol and redeem them and take the reserves, so the X and Y token reserves, into their own protocol. And then they will issue not just the VP rewards, the vampire protocol rewards, but also new liquidity pool tokens from this vampire protocol. And in that way, it tries to train the original protocol and effectively become the more important liquidity provision protocol, the more important constant function market maker. And this is, of course, it can potentially work, because when you think from the point of view of the traders, they always want to engage with the constant function market maker that has the least slippage, essentially. Of course, it also depends on the fees, but assuming that the fees are the same, then you want to engage with the protocol that has the highest liquidity and therefore has the lowest price slippage when you are conducting a trade of a given volume. And in that way, it's of course, as soon as you are the dominant protocol, then it's super hard to change that. It can happen for several reasons, but since the traders, they have an incentive to trade with the largest one for a given pair, and of course then in correspondingly, the liquidity providers also in many cases have an incentive to go to the largest one because most of the trades are there. Now this depends, of course, it's always relative considerations, but in many cases, when they're really the bulk of this trading activity is on one protocol, then most of the liquidity obviously will also go there. In that way, it's a super interesting attack on this original protocol. This really launched this whole notion of protocol wars, where there are forks and alternative versions of these protocols, and they are essentially battling for the attention of the users, for the liquidity of the users, and that these vampires attacks were one of the earliest versions of that. If you want to look into an actual example of that, look at Sushi Swap, which in this case happened to be the vampire protocol, and an earlier implementation of Uniswap that happened to be the victim. And that really was something that got a lot of press coverage, also has been analyzed in some academic papers. So it is a good example of these liquidity mining and vampire attack scenarios. And then the last thing that's also loosely related to DEXs are initial DEX offerings. That's the idea when you want to issue a new token, when you want to create a new token and you want to sell it, and you don't know exactly the market price and you need a good way of selling it, then a DEX might actually be a good option, the constant function market maker to be more specific. So here you have the curve on the left side once again. And you're starting out in a situation where you have a given amount of X tokens and you're also depositing Y ETH into that new pool. And since you are the only one initially who has these X tokens, of course, there isn't any possibility to go further to the right from this initial point. But what can happen is that people are starting to buy these X tokens, and for every single X tokens they buy, of course, the X token holdings of the pool will decrease, whereas the ETH holdings of the pool will increase, and therefore the tokens get more and more expensive. It can also happen the other way around once there are some of these X tokens in circulation. So when we are at a certain point left to the initial point, then of course there will be other people who also have the X token, and if they feel that the token got too expensive, that it's overpriced essentially, then they can sell their X tokens and take out some ETH, realize a profit. So this initial DEX offering allows you to have a market price discovery scheme for new tokens, for newly created tokens. And there are many examples, but one example you can look at are Unisocks. So it's a token, it's essentially tokenized socks from the Uniswap protocol that allowed you to redeem these tokens for actual physical socks. And that's something that has been launched in this way. So where the earliest tokens there have been relatively cheap, and then later on these socks or the tokens of these socks got ridiculously expensive. And that's what's called the initial DEX offering. Also, as you will see on the next slide, I think, one of the examples in our problem sets, you could say, is actually an initial DEX offering, because we will list the crypto lectures coin, of course, on a test net, so not an actual mainnet, and just for you to play around with. And since as of right now, none of you has these CLC, the only thing you can do when you're interacting with the CLC DEX is depositing some of these test ether to the constant function market maker, and thereby withdraw some of these CLC. So you could look at that also as a version of one of these initial DEX offerings. All right, and with that, we are ready to tackle the exercises. And for the exercises, we will use Uniswap, which is an implementation of a constant function market maker. Make sure that you are connected to Ropsten testnet. And then what you can do in exercise 1 is you can create a new pool for your own token. So the token you have created as part of the ERC20 video, you can actually list that now on Ropsten testnet's version of Uniswap. And then you can make some swaps. And of course, if you want to provide additional liquidity and remove liquidity and so on, just basically play around with the newly created pool. And there is an optional exercise. What you can do is we have given you on this exercise sheet right here the address of the CLC token. So that's the CLC token address. So that's the token I have created in a previous lecture. And what you can do is, again, connect to Uniswap on Ropsten testnet and then make some swaps and provide remove liquidity from the ETH CLC pool. Of course, initially, as I said, you have to make a swap because you don't have any CLC tokens. But what you can do is you can provide some test ether, take out some CLC, and then later on provide the liquidity when you have the combination of ether and CLC. And again, you will find the pool by using the token address below. Now in the solutions, when we look at the solutions, then I will not specifically go through exercise 2, because effectively when you look at the two exercises and the nature of the two exercises, since the example, the token I have created happens to be the CLC, it's effectively the exact same thing for me. For you it's a little different, because first you can do it with your own token and then you can connect to the token someone else, in that case me, has created and play around with that token or the exchange thereof. All right, and here you have some additional references and recommended reading. This is something that can help you when you are interested in the topic, when you want to get some additional information. It's a good starting point, for example, if you want to write a thesis, a master thesis, for example, on these topics, but it's not something you have to do for the preparation for the exam in the context of this class. I want to be really clear on that, because that's a lot of reading right here. It's just some service to you that you have additional reading when you're interested in the topic. Now, with that, let's look into the solutions to the exercises. Alright, so the first thing you do is you go to the Uniswap webpage that is referenced on the slide deck, and you make sure that you're connected right here. You also check that you're on Ropsten, and then you can select your token. You paste your token address, it shows up, so CLC in my case, I import it. You can ignore this warning because you're on testnet. For mainnet this would be important, of course, and then you can see the token reflected here. Now, obviously the pool does not exist yet, so you have to click on pool, and you have to create a new position. And here you can pick the token again. So we pick CLC, we have ETH as the other asset, and we go with the regular 0.3% fee, so that's the standard. The next thing we have to do is we have to determine the price ratio. And what we're saying is that 1 ETH initially costs 100,000 CLC. Here we go with an infinite range, so from quasi zero to an infinite price ratio, and then we initially deposit 300,000 CLC and 3 ETH. Now recall that CLC is an ERC20 token, so if you want to interact with the contract, we first have to approve, basically give the contract some allowances in CLC. That's what we're doing with this transaction. And now we check it on the block explorer really quick. And it looks like it's already indexing, so it shouldn't take too long. It actually got already confirmed. It's just indexing on the web page. And here we are. Here we see the success with already 2 block confirmations. Now, when we scroll down, you can also see right here that this is an approval. You can see that it's an infinite approval because the amount, the value was just a bunch of Fs. That means it's the maximum. Now we have the second transaction, and here we're actually contributing the value. So we have these 299,900 CLC and 2.999 ETH we are adding. That's what we're doing. Second transaction, and now the constant function market maker can actually withdraw the CLC from our account because we have approved that as part of this second transaction. Again, it's already indexing, and here we have the confirmation. You can see that we have sent 300,000 CLC and 3 ETH. It converted it to wrapped ETH, and that's what we got in exchange right here. It's an ERC721 token that essentially is our pool token, so the liquidity pool token. Now when we go to the token page, you can see that we have a new holder, so we have 4 holders now. This holder, you can see it right here, has 300,000 tokens. That is the constant function market maker. When you click on the address, and you can do that right here, and then you can see that these are the token holdings. So you can see that there are 300,000 and almost 3 ETH in the contract. All right, now we have initiated the pool. You can also see it here as our position. The next thing we have to do is a swap, and we go back to the swap tab. We pick the CLC once again, so we have the ETH CLC pair, and since it has already been initiated, we can trade now, and we'd like to swap 0.5 ETH, 0.5, and that's the price we get. So it's 42,746.9 CLC we'll get. It warns us that we have quite a slippage, which is not surprising because the liquidity in the pool isn't too high. We do it anyways for demonstration purposes, and since it's testnet. And here the transaction is already indexing again, so it should be reflected any moment. And here we go, that's the confirmation. And you can see with the tokens transferred right here that we have transferred 0.5 wrapped ETH because I converted it in the background as part of the composability, and we got these 42,746.93 CLC. All right, now that was a great opportunity to list your token on an exchange, to swap, to provide liquidity, or remove liquidity. So basically just play around with your token on a decentralized exchange. And it also was a great example of a Web3 front end. So you have seen how in this case, the Uniswap front end interacted with your Web3 wallet with MetaMask and got the information from the blockchain and also sent transactions to the blockchain. And I think that's something that is really exciting and gives you a relatively good understanding of how many of these decentralized finance protocols and applications look like. With that, stay curious. See you soon.